Awesome. Thank you so much. I just want to also say thank you for the invitation to be here. This has been a wonderful project to be a part of, and it's an incredible opportunity to share some of our findings. So indeed, I'll be discussing some distributions associated with probabilistic computing. This is joint work with both Darby Smith as well as William Severa at Sandia National Labs. And so maybe a first place to start is to have a conversation about randomness. That seems like a good place to start. So modern computing is it's largely a deterministic field. We don't like randomness inside of our computations. We prefer things to be somewhat predictable or deterministic. This allows us to be able to sort of make conclusions that we can expect to see. We don't have to deal with any sort of unexpected issues. This, for example, is the key benefit of what's called digital electronics, right? But honestly, sometimes randomness really, you can't remove it all. It's going to be present whether you like it or not. And so, yes, you can live in an idealistic situation where you pretend that randomness doesn't exist, but it's going to be there. And you're going to get a more accurate understanding of the situation if you can learn how to sort of understand and harness this randomness. And so this is useful in modern things like algorithms for scientific computing, cryptography, as well as if you want to take probabilistic approaches to solving different physics problems. And learning to understand and harness this randomness is going to be a fundamental sort of objective in order to understand these types of settings and the tools that we use to investigate these types of problems. So, to that end, if we want to understand randomness, it's probably going to be useful to force randomness to occur in a systematic way so that then we can assess it and get a better understanding of what's happening. There's a couple of ways to encounter randomness with regularity. We'll start with what I'm going to call the naive approach. So the naive approach to understanding this, I think, would be something that we've all done at some point. You take a programming function like random. So this is a so-called random number generator. The only issue you have if you spend more than 5 seconds using this is that you observe that this function will produce a quote-unquote random number. It'll do it really quickly, actually. However, it's really not that random. It just appears random, which to our naive human eyes feels fine. But if you're going to do this on sort of a massive scale, this notion of what we'll call pseudo-randomness is not really appropriate. This sort of approach uses what's called a seed, and so it has some sort of a seed that's typically difficult to replicate. It's usually, for example, based on like your system time or something that someone who's using the code or observes the output would have no idea what the seed was. But the entire random number you're getting is determined based on that seed. So this is still deterministic in nature. Some fun consequences of what can happen if the seed is known to the user is you can do different manipulation. And there's fun things that occur if you want to look at this. Depending on what your hobbies are, you can look into things like in Pokemon games, particularly older ones, you can take advantage of understanding the seed in order to manipulate the game to do different things. Over here on the right, we have Minecraft speed running. Whereas again, here you can look at different types of speed running. There's set seed and random seed, all about whether you know or do not know the sort of random predictable things happening based on the seed. Of course, these are fun objects based on fun hobbies. We're going to do some more powerful sort of observations. But I think these are fun ways that randomness manifests itself inside of the world around us. That said, these are what I called pseudo random number generators. We'll call them PRNGs for short. And these are not suitable for truly random analysis. So when I called it a naive approach, this is sort of what I'm getting at in a technical sense. These are deterministic based on the seed we talked about earlier. So the alternative that we want to have, if we want to actually understand randomness in a reasonably cohesive way, is we want to use not pseudo-random number generators based on deterministic seeds, but instead we want to look at what are sometimes called true or mechanical or hardware random number generators. For this talk, I'm going to use true as the appropriate word, so those will be shortened to TRNGs. These are devices that will produce random numbers not based on a seed, so they're not deterministic. This is usually using some natural phenomenon that you can utilize to produce randomness. Classically speaking, these tended to be things like coins and dice. And yes, I hear some of you in the audience here balking at this, saying, well, wait a minute, coins and dice are not necessarily completely fair, depending on insert argument here. That's fair. That's okay. I understand where you're coming from. So instead, the modern approach is not to use exactly coins and dice. Modern approaches use more sophisticated machinery. For example, they'll use things like thermal noise, Brownian motion, things like the photoelectric effect and quantum phenomena. This picture, for example, is a sort of cartoon illustrating how the photoelectric effect works. You have, and I am not a physicist, so keep that in mind as I talk about this. But the light here comes down, hits a nice metal surface inside of a vacuum, and then as it hits that surface, there's some sort of electrons refracting out of it and things of that nature, and sort of the direction that the electron is headed is random. And so we can somehow have some sort of a detector on the left-hand side, and where those electrons are and when they show up is going to be random. And you can use this sort of a setup in order to pull random numbers. And maybe it goes without saying that this is really expensive. And that's fair, but this is the price you pay in order to have a truly random sort of number coming out of your device. Some other modern examples are stemming from recent efforts to understand neuromorphic and quantum computing. And the true random number generators that are coming out of this investigation would be, for example, memoristic devices, p-bits, and then tunnel diodes or magnetic tunnel junctions. These two objects I've highlighted in blue here. I have a cartoon here illustrating sort of how these devices operate. These pictures are definitely not mine. These are credited to the paper given down here. But these two devices have been of recent interest for a myriad of different reasons. The reason we're interested in it is because they are actual genuine devices that produce random numbers, and in particular, they both can be operated in such a way that they act as what we're going to call a coin flip. We'll see the definition I'll use for that in a moment, but what this means is that informally, the outputs you get from these devices, they can be operated so that the outputs look very binary. They're going to produce either one outcome or another outcome, and which one it produces is random. And so this is a great way. These are great physical devices that currently exist that are producing data that, as a mathematician, I'm very interested in analyzing. So if these can be operated to act as coin flips, we might want to ask, why coin flips? Of course, many of us are familiar with coin flips and why those things are interesting, but a formal definition for what I look at as a coin flip is a coin flip, or what we'll call a Bernoulli random variable. This is going to be any device that has the probability of producing two outcomes, say heads or tails. And in particular, we'll let p sub 0 be the probability of returning 0 or tails. And then, of course, p1, the probability of returning the other side, is just 1 minus that value, because these probabilities are adopting real numbers between 0 and 1 inclusively. And so these sort of setups are useful because, for example, a coin flip with any sort of fixed probability of tails can be manipulated to provide samples from any coin of any bias. So coin flips can be used to produce any sort of other types of fair or notably unfair coins of your choosing. This can, of course, be exploited to return a sample from a variety of different probabilistic distributions. which we find very interesting. I find very interesting as a mathematician. They can also be used to approximate solutions to different NP-hard problems, for example, max cut, but I'm not going to get into that sort of application. And so what we're interested in is taking the notion of coin flips, and then we're asking questions about generalizing from coins to what we're going to call Q-sided dice. And this has had some interest recently, for example, in different efforts to analyze self-learning neuromorphic hardware. There's some interest in that direction where the different hardware devices they're building are producing sort of multi-well outputs. So they're producing not just binary one outcome or the other, but a variety of different outcomes. And some observations we can make about dice and why we might want to look at them is that dice are better than coin flips at bit precision. For example, if you take a two-sided coin, flip it 8 times, look at all your possible outcomes, you get a measly 256 outcomes. Whereas if, for example, you take the same 8 rolls of, say, a 5-sided dice, the number of possible outcomes increases by orders of magnitude. We have 390,625. And so if you were to, say, be in a setting where a flip and a roll cost the same, meaning the energy cost and whatever that means for you, then the dice roll with way more possible outcomes would give improved bit precision. And so it could reduce errors and things of that nature. So dice could be useful in that regard. And also recent simulations of ours suggest that dice are more resilient to dependent behavior. These 2 diagrams we have here are based on some initial data that we've pulled. And what this is modeling is what we're going to call latching. So what that means is if you take, say, a coin, a possibly unfair, probably unfair, and then you flip it, well, when you flip it a second time, there's going to be sort of this underlying question of when you flip it a second time, is the second output dependent on the first outcome? And the notion of latching is the question of whether when you flip the coin a second time, will it actually flip or will it stay the same? And it turns out here we have on the left some data based on flipping coins. Here on the right, we have data, for example, 5-sided dice. And the important note from these 2 pictures is if you do look at the y-axis, over here on the left, these values go up to 0.25. Over here on the right, the values are much smaller. We see 0.08. This y-axis is modeling the deviation from fairness. So depending on what the latching probability is, and depending on sort of how unfair your coin is, what this is measuring is how likely your overall data is going to be fair as you flip your coin or roll your dice multiple times. And the idea is that the picture on the right, these output lines we have for dice are the deviation from uniform, the how fair it is suggesting that it's way more fair on the right than it is on the left. So this tells us that somehow the dice are a little bit resilient to dependent behavior. It's still producing sort of uniform outcomes, despite having some latching hiding in the background. So all this to say that we want to argue that Q-sided dice are useful and interesting to study, in addition to the coin flips, which are coming from our device data that already is out there. And so what I'm interested in as a mathematician is the following question about any sort of device that we build, whether it's producing coin flips or whether it's producing dice rolls. The question I have when someone makes this is it fair? Are the outputs it's producing truly random? Or are the random numbers that it's producing, does it have some sort of latent bias or some sort of inherent unfairness hiding in the background? Well, my goal and our goal as a result is to use mathematical investigations to understand a given device's departure from uniform or fair. And then if we can understand whether a given device's outputs are fair or not, well, then we can make better devices. But then if we make better devices, then we can pull data from the better devices, and then mathematically analyze that again to get even better conclusions about the device's outputs, which then better informs the creation of more accurate devices, and so on and so forth. And so to me and to my team, Darby and William, we feel that having a rigorous mathematical understanding of the outputs, the outcomes of these devices allows us to make those better devices. So this is what we're calling mathematical co-design, that we enhance each other's understandings along the way. So with all that said, the name of the game for us is it fair? From a mathematician's point of view, this question has two parts to it. The first part is what I'm going to call the probabilistic part. This is all about establishing the theoretical framework surrounding the distribution of outcomes that we get from pulling data from a true random number generator device. Another way you can think about this is if you have a known device, it could be fair, could be unfair. We want to know what the probabilistic framework is for that device's outputs. The second half of the mathematical investigation would be what I call statistical. So this is taking a device, taking its output, and we know probabilistically what we expect to see based on the device's data. The statistics would then come in second, and that allows us to run things like hypothesis tests to determine how reasonable those outcomes look like, and we're testing it against that probabilistic framework that we've developed. So this is taking an unknown device, comparing its outputs to the known framework, and then asking, is it fair? So what we've done so far is largely answer the first part. This is the probabilistic framework. Then we're going to focus on some statistics. For this talk, however, I'm only going to talk about the probabilistic stuff because the statistics is still ongoing, and we don't have anything with that. Well, we have some things, but it's not sort of ready to share at the current moment. So the probabilistic framework needs us to mathematize the situation a little bit more. So we're going to call this Bernoulli modeling. So this is understanding. We're going to start with coin flips, and then we're going to generalize to our dice rolls. So if we flip a coin, and so, for example, you can think about this as soliciting input data or output data from a device. Remember that those tunnel diodes, for example, can be operated in such a way that they produce coin flip data. So if you solicit that device and you get some sort of output, that's going to be the equivalent in our mathematical framework of flipping a coin. And we're going to take multiple draws from our device. So we're going to equivalently flip a coin over and over and over again. Mathematically, we're going to let those, in this case, we're going to let the tails be 0, the heads be 1. That's what we talked about earlier. And if we do flip a coin in this case over and over and over and over again, this is going to produce a bit string. This is a sequence of zeros and ones. So for example, here we have a finite bit string, 100 or 11010000. The way you want to think about that in this little cartoon is converting or taking this bit string and interpreting it via binary. So what that means is that each of these numbers is serving as the sort of switch that either turns on or off the associated binary contribution. So every time we see a 1, we keep that power of 1/2. Every time we see a 0, we destroy that power of 1/2. And so if we add up all those powers of 1/2, that means that this bit string is associated to the following real number. I add up those powers, boom, I get 0.8125. And so that output, which is the sum of each of these binary contributions, and then the zeros and ones, the outputs of my coin flip, is what we'll call the xn's. Those are those coin flip outcomes. This sum, a finite sum in this case, is exactly associating to this sequence of outcomes some real number. Of course, inside of the framework we're working with, we're not necessarily going to want to always work with a finite example. We want to envision what's going to happen if we take a bunch of information from our device. What if we take, for example, mathematically, we'll investigate taking an infinite number of draws. This framework will still support that insofar as now we're going to end up having an infinite sum, and this infinite sum will produce still a real number. It may no longer be rational like what we have here, but that's fine. There's nothing wrong with that. It's still just a real number between 0 and 1. So this is viewed as the binary encoding of that number. And so the approach that we have here is we're going to take a possibly unfair coin. We're going to toss it possibly infinitely often. And then we're going to record the outcome as a bit string. We convert that bit string, interpreting it as a binary representation of a real number. We're going to then associate every output, we're going to associate to every infinite sequence of outputs of our coin with a real number between 0 and 1. And we want to know the distribution of these binary encoded outcomes. Specifically, if we're going to do a probabilistic endeavor, we're going to want to understand two things: the probability distribution function and the cumulative distribution function. Now, I hear what some of you are saying. Some of you are sitting there and you're saying to yourself, I don't remember what those things are, but I did one time know what those things were. That's fair. I understand where you're coming from. Let's have a quick review. So the probability distribution function is essentially, it's just a histogram. This is just recording the frequency of outcomes. And so you can imagine here we have a situation where I have an actual sort of histogram, and then I get way more data points. There's my histogram. And if you kind of look at this and you imagine taking an infinite number, you can sort of, I don't know, connect the dots in some sort of a way, and boom, you have a nice smooth curve, nice and differentiable, maybe. And so over here on the right, we're going to investigate the area underneath this probability distribution function that we have here. And the area underneath that region is telling you the probability that whatever outcome you're looking at is going to sort of lie in that region. So if we investigate that a little bit further, the probability is going to be computed by taking this area, which of course we know, Calc 1, that's going to be the integral between, in this case, 0.2 and 0.3, for example, of this probability distribution function. If we use this boldface P to denote the probability that our outcome X lies within that region, then we can investigate this area by using the difference between two improper integrals. We can take the area from the bottom left all the way up to whatever chosen X value we want. That's going to be this integral. And of course, then the area trapped in this blue region is going to be the improper integral up to 0.3 minus the improper integral up to 0.2, and that's what we get here. So this F we have, this accumulation of area all the way up to our chosen X value, is what we're going to call our cumulative distribution function. And so the probability is taken as sort of, it looks vaguely like this fundamental theorem of calculus business. So at its core, all of this is just really fancy Calc 1, but with a sprinkle of probability hiding on top. And so this will be the CDF that we're interested in looking at. So let's talk about the coins and the data that we were able to pull initially. So if we talk about the PDFs, which again, just a histogram, this is just telling me the frequency of outputs. This is a smattering of different data that we were able to pull. For example, down here, we have the probability of heads is 0.5. So that's a fair coin. So of course, the probability distribution should be flat because everything is occurring with the same frequency. Cool. Over here on the right, we have, okay, I flipped 64 coins. The probability of heads is slightly unfair. It's now 50.5% heads. And what we see is that the PDF, the histogram, seems to be bouncing around everywhere. If I make the probability even worse, say 0.6 or 0.4, we see that it really starts to just get really noisy, which is what we have going on over here. We can ramp this up a little bit. We can look at 256 coins or 1,000 coins, and it gets really noisy really fast up until you hit a point where, for example, we flipped a lot of coins over here and the probability is really unfair. So now it's 30% heads instead of a nice 50-50. What we see is that numerically, our histograms collapse. They just immediately collapse, except for this sort of small number of spikes that we have, which is really unusual. And so if we're going to ask questions about the CDF, this is going to cause some problems. Because if we flipped a bunch of coins, the PDF collapsed outside of a handful of points. Let's just call that dust for now. It's just a very, very small scattering of points. And so if I want to integrate this to get my CDF, integrating this is mostly nonsense. If you want to talk about the things like Calc 1, right? We're going to do Riemann sums and all this fun stuff. This curve, if you want to call it that, is flat almost always, and it only spikes every so often. This is not a thing you can integrate directly. But the CDF is still something we want to understand. So we can do numerical analysis. And when we did that, we saw over here, for example, that the orange line is what you'd expect if you had a fair coin. And here, the blue line seems to be numerically the CDF, the integral of this PDF, which it seems to deviate. We know it's going to deviate from fair. But the question is, what is that function? Can we write it down? I mean, I want to analyze this thing. I want to do math on it. I'm a mathematician, after all. It turns out the answer is yes, but not in a closed form. You have to do it recursively. For coin flips, this was already done in the past by Billingsley as early as 1995. And he showed that indeed the CDF you get from flipping a coin infinitely often, it can be given recursively by this formula. I'm not going to go into why that formula works. It works, and it produces the outcome that we were looking at. For example, here, for a myriad of different unfair coins, these are the cumulative distribution functions that we end up finding. And what we see, if you look at some of these pictures, is they look very fractal-like. They seem to be self-replicating as you zoom in, which is interesting in and of itself. And what Billingsley shows is that, in fact, these distributions we see here are what he's calling singular. I'm going to define that later. So I highlighted it in blue because I'm going to recall that later, I promise. But this was the main idea is, okay, we have a formula for generating the CDFs for coin flips, which is useful. Now we can understand what it looks like. It's still the open question we have now is, okay, Billingsley did this for coin flips. There's reason for investigating Q-sided dice. So what about dice? Then what does the CDF look like? We're inspired by Billingsley. We think it's probably going to be able to be written recursively. And it turns out, yes, last year, the three of us were able to establish this formula for if you had a Q-sided die and you wanted to figure out what its associated cumulative distribution function was. In fact, we were also able to show that it was singular if the die was unfair. Again, I'll define that in a moment, I promise. And so we were able to take this Billingsley result and generalize it to Q-sided dice, which is great because this allows us to actually analyze the probabilistic framework that we're getting from these devices, which is fantastic. Small thing that might be interesting to some of you, depending on your background. If we let the die be three-sided, and we choose this very specific choice of probabilities, 0.5, 0, and 0.5, this is what we get if we plug it into our formula. And if I iterate this process, because it's defined recursively, this is the sequence we get. We start with an x, which is just that nice y equals x that we have there. And if I iterate this once, I get this nice maroon function. It's piecewise linear. Looks a little bit like what's called a step function, but don't worry about all these vocab words. And then if I iterate it again, I get this blue function. And so it seems to be sort of slowly but surely turning into this type of picture that we saw down here. But if I do iterate this over and over and over, I get these flat portions in the middle. And then all of a sudden, if I do this over and over again, we get this picture. And depending on your background, this picture is either nothing to you, or it's something very specific to you. This is what's called the devil's staircase. This is exactly the mathematical object that you would investigate if you wanted to understand a function that is continuous. However, it increases on what we call dust. Technically speaking, a set of Lebesgue measure 0. This is a famous example inside of mathematical analysis, and the fact that we were able to recover it organically using this Q-sided probabilistic information on unfair dice is fascinating. It links us into a wide variety of existing mathematical literature that helps us better inform the development of these devices. So at this point, we're very excited. This is a bombshell of a discovery. Why does this work? Well, why is this the expected outcome, I should say? Well, this was our PDF, right? We saw that a PDF only spiked at a dust-like set. Well, if I integrated this, what that means is that the area should really only be increasing on this dust-like set, and we should be flat. Our area is not accumulating anything on these other regions. So the integral will only increase on this dust-like set, and that's exactly what we saw inside the devil's staircase. And this is exactly what singular means. This means that your distribution is increasing on a set of Lebesgue measure 0. You don't have to worry about Lebesgue measure 0. All you have to worry about is that it's increasing very seldomly, which is a fascinating mathematical discovery, because this picture that we had earlier, this picture we got via numerical analysis, this is actually flat pretty much all the time. The way I describe this type of phenomenon to my students is I say, if you took a dart and you just like threw it at this picture, almost always, basically the entire time you throw that dart, it's going to be on something that's flat. It doesn't look like that because numerical analysis is really bad at understanding this, but that's what it is. And so as a result, numerical analysis was failing. And that's why we wanted the analytic approach. We needed some mathematical underpinning to understand what our numerical approach wasn't understanding, which is great. Now we know why this thing is broken and we can figure out workarounds. And so the question that we have now is, okay, I know what the CDF looks like. It's that blue thing. I can write it down. It's written recursively. But that orange thing that we have here, that orange thing was what we expected if we were fair. So let's bring it back to the beginning. Somebody makes a device, and the device that they make is producing random outputs. If we suppose that the outputs are being modeled with, say, a 7-sided die, I don't know that they made a fair device. They think they made a fair device, but we would like to test that. Well, if it's fair, then ideally the CDF should be the orange line. But if we solicit a bunch of information, some data from it, it might be producing this blue line. And so we have to ask, did we just not pull enough data? Or is it secretly unfair? If it's unfair, we need to tell the person that made the device that what they made is not actually as fair as they think it is. So we need to find a way to compare these two functions with one another. And that's exactly what we embarked upon next. Turns out there's a myriad of ways you can compare these two things, but there's two ways that we were able to get some traction. And that's using the soup norm as well as the arc length. So what that's calculating, the soup norm is going to be calculating sort of the maximal distance between these two lines. And then the arc length is going to, well, it's going to tell you how long the measurement of that blue line is. And we can compare that to the length of the orange line, which we know is going to be root 2, because it's a nice straight line between these two values. And so we tried to work toward understanding what these values were. We discovered, for example, that if you have the recursively defined CDF, the blue line here, we know that it's given recursively, like iterating these functions we saw earlier. And it turns out that the absolute deviation between your blue line and your blue curve and your orange line that's given right here is no worse than some constant multiple of how far away the first iterate, this X line here, so that's the orange line, that's the fair line. It's no worse than some constant multiple of the distance between that fair line and the first iterate, which in this picture is that maroon function. All other iterates will get closer and closer and closer and closer to the uniform. And so as a result, we have a nice upper bound on how poorly your CDF, the blue one, can stray from uniform. In addition to understanding that deviation, we do have an arc length understanding. The arc length is, again, the question of, well, if I know the orange line's length is √2, what is the length of the blue line? Calling it a line is, of course, a misnomer. It should be a blue curve, but it looks very line-like. You may look at that and say, well, it's obviously got to be really close to √2. I mean, just look at it. As a mathematician, the minute somebody says, look at it, and we're dealing with an infinite process, I'm immediately concerned because infinite processes can behave in awkward ways. And this is no different. The arc length of that blue curve, we can prove, is a 2. We do have a formula for computing that. Here we have a formula for computing the arc length of the nth iterate, this nice polygonal function, and then we just take the limit and we get that nice value of 2. So it's very, very interesting. The blue one has arc length 2, but the orange one has arc length √2, despite looking super similar. So there's a lot of interesting phenomenon hiding underneath all of this, and our goal is to try to leverage these sort of comparisons to again assess the fairness of the outputs that a given device is producing. So with both of these, we had the sup norm, and then we had the arc length. Another question that you can have is not necessarily, like we did here, comparing the uniform output to a possibly unfair output. The paradigm we have here is I have one device and I'm taking a look at outputs and I'm comparing the outputs to what I would expect if the device was fair. So here I'm comparing one device to the fair ideal. It stands to reason that, well, what if I had one device, it could even be unfair, but I actually really, really, really know it. I know it really well. The individuals I speak to, they are just beyond confident that they know this device and they know exactly how the distribution of its outputs work. And so I look at that and I say, okay, cool. If you know the device's outputs are fair or unfair, and you're just super confident, what they may be interested in doing is saying, okay, let's take this device that we understand really well, and instead of so we're going to take the device that we know really well, and we're going to take another device that we don't currently know that well. The analysis we've done so far is taking the new device and saying, is it fair, by comparing it to the uniform, the fair ideal. But maybe you could say, well, I know this other device really, really well. Maybe I can use that other device to check the values of the unknown device and kind of see if I can't get any information out of the fairness of the new device by using the known, possibly unfair device. This might seem reasonable depending on sort of your setting and your framework. Nope, can't do that. That won't work. We were able to establish that if you have two different devices producing the same, say, number of outputs, so they're both, say, producing things that model 5-sided dice, even if, you know, if they're both unfair, even if you know one of them really, really well, the conclusion is that, and we have it written here in the technical verbiage, the probability measures are what's called mutually singular. So what that means is that if you look at the probabilistic framework of one, it literally cannot ever possibly inform the probabilistic framework of the other. They're operating with different sort of domains. They just won't interface very well. So no, the answer is if you know your device really, really well, you can't leverage that to know other devices. Sad day. Now, granted, the way that this was all written is this assumes that we have two devices that are producing same-sided information. So two different devices that are producing information that looks like five-sided dice each. Maybe you sit there and say, well, what if I have a seven-sided device and you have a three-sided device? You told me that the two seven-sided dice can't compare, but maybe I can compare a seven-sided to a three-sided. Fair question. We don't know the answer to that at the current moment. Our guess is that if the two-sided devices are different-sided, that again, you can't compare them unless one is the power of the other. So if you have a four-sided device, if you will, and a two-sided device, then there is a comparison because you can convert things from base 4 and base 2 and stuff like that. But the general question about our comparing arbitrary sides, we don't know. This is still an open question. So overall, through the course of this conversation, we've investigated the probabilistic side of what we're looking at. We have established the theoretical framework for the distribution of outcomes from testing one of these devices. We have the coin flips. We have it for Q-sided dice. We know what the cumulative distribution looks like. We know what the probability distribution looks like. We can compare them to fair outputs in two different ways, no less, using the uniform deviation from the absolute deviation from uniform, this so-called soup norm, and we also were able to do it using arc length. So it stands to reason that the next objective is going to be the statistics. Now that we know what we're comparing things against, we need to actually take some raw data and run some hypothesis tests and see how all that sort of shakes out. Overall, that's what we have so far. And I want to say thank you to all of you for taking time out of your day to come join me and learn a little bit about our recent endeavors. And thank you again to the organizers for inviting me and giving me the opportunity to share with you. So thank you again.